Hi. We like to do this video live, and I have actually had an attempt at doing this video live, but I'm in a hotel and the bandwidth is really not up to, it's just not up to it basically. I'm also doing this video early, which is also unusual. So we like to do this video 8 a.m. London time every week, but there's so much travel going on at the moment. I'm in California, the time zone mess up, a lot of meetings, so we're having to record this, and though having attempted to do it live, I'm going to have to record it and upload it. So ZP, every week we like to do this webinar, 8 a.m. London time. We should be doing this on the 10th of November. We're actually doing it the 9th of November, and we're doing it, as I say, in California. Don't forget the ZP Academy. The ZP Academy is a great way of finding free information. There's at least 2 courses on there that are free, which are a great way of learning about electrochemical biosensors. There's webinars every week. This is one of those. We do have collaborations. We do have jobs that are posted. We do have the ZP Developer's own website, and we do have workshops. Now, the workshops we do have, the next workshops are actually in India, and my colleague is flying out there, and I will be coming in online. We also have a workshop in California, hence this is why I'm here. We also have workshops in Norway. We also have workshops in Coventry. So if you are interested in screen printed electrodes and making IVDs, in vitro diagnostics and screen printed electrodes, I think that one in Coventry is particularly useful. And then we have workshops also in France, in Grenoble. If you see a link, then I'll put the link underneath the video, and that will help you to find the information later on. So we've had 2 sets of questions that have come in this week. Question number 1 is about screen printed electrodes, and question number 2 was about measuring lactate in sweat. I will speak fairly fast. So question number 1 actually had a whole series of questions. And the first question was, this person wants to do 2 electrodes, or maybe 2 working electrodes, or maybe even 3. It's not a concern for us about whether you want 2, 3, 4. There are concerns about basically footprint. How small can you make this device? And I will sort of discuss that. Question number 2 is, why do we use rectangular electrodes? And it's because we're seeing ahead of where the product is at the moment. So, for example, many R&D electrodes are designed purely for essentially academic research, and they weren't, they're easy to pipette onto, they're easy to add the samples to, but there's no thought about how those electrodes will actually work in a flow channel, for example, and that's something that we do think about. By the way, these rectangular electrodes, the biggest consumer of Zimmer & Peacock screen printed electrodes is Zimmer & Peacock. We're a contract developer, contract manufacturer. We're ISO 13485, and actually we do these kind of assays all the time on our electrodes. I do have a little image to share on that as well. We can do customization in probably about 6 weeks. Previously, they were using an electrode from a different vendor, which had 2 working electrodes, a counter and a reference, so they needed a connector for a 4 electrode system. We would have to do that bespoke. We have connectors for 3 electrode system. I made the comment earlier on that we are the biggest users of our own electrodes. This is one of those rectangular electrodes upon which we made an immuno assay. We've actually made the immuno assay by hand, but we also use these electrodes a lot in molecular assays. It's not true about circular electrodes. They have advantages, but the advantages are at the R&D stage, and the R&D stage doesn't necessarily translate into a manufacturable product. And I have a quick link and I'm just going to move myself out of the way, and I'll put the link also underneath the video as well. Question number 5, I needed to increase the pack size. So we make these mediated electrodes. They were only available in pack sizes of like 10 and then sort of 1,000, so I made a pack size of 500, fine. And also, we do have connectors. So, for example, we have mediated electrodes, carbon electrodes. We do have connectors. So the connectors have kind of 2 variables on them. It's the slot size at the front. So if you're using one of our mediated electrodes, you need a 7mm slot. And then the connectors on the back are either going to be 2mm or 4mm, depending on the vendor that you got your potentiostat from. So you just have to measure the banana plugs, or I've got a little note on the website about this as well. And there's also a link, so hopefully that will help. this is almost like a rhetorical question, but what's wrong with screen printed electrodes? I do have an entire note about what's wrong with R&D, I should say, screen printed electrodes. So I have sort of looked into this and discussed it a lot. Many of these circular electrodes, the footprint of these electrodes is simply too big. I do have a price calculator on the website, and I'm going to talk about that in a minute. But they're simply too big, and so when you go to manufacturing at scale, they still look too expensive. The smaller you make something, the less material is used, the higher the packing density within the manufacturing process, and therefore we can make them lower. Many electrodes are not designed with microfluidics in mind. This is crazy. They're just designed for the R&D phase, but there's no thought about how is that going to fit into a microfluidic cartridge. Circular electrodes are really designed for R&D dispensing and not necessarily manufacturing. I have said that point. What's wrong with R&D screen printed electrodes is often the quality. What is not said is everyone expects a low price, and they can get that low price. But low price and high quality only come when you've got high volume. And so a lot of these R&D electrodes that you find on the market, there's not an intrinsic high volume production behind them. So you find batch to batch variation, and you find within batch variation. So there's a real sort of quality, and that's because people expect a low price, because this industry is what you call as commoditized, that people have sort of an expectation that I'll pay a low price, I'll get a consistent product, and it's not the commoditization that they think it is. One of the big problems with R&D electrodes is people are viewing these electrodes sort of in isolation. You know, at Zimmer Peacock, if we're making an electrochemical assay, whether it's enzyme-based, immunoassay, whether it's molecular, you have at least 4 parameters, actually, when I think about it. There's 4 parameters at least. There's the there's the screen printed electrode, there's the functionalization of that electrode, there's the excitation of that now sensor, and there's the extraction of the data from that sensor. So when you go to a screen printed electrode manufacturer, the only thing they're taking care of is one of those components. And actually you can share things like precision and accuracy by dealing with all 4 of these components: the electrode manufacturing itself, the functionalization, the excitation of that electrode or sensor now, and the extraction of the information from that sensor. You have to do with all those 4 things essentially in parallel, because otherwise you're just trying to put all your precision and accuracy requirements on just one component, when actually you have to share them across all 4 components. So we do take a much more holistic approach, which generally means that we only work well when we're really sort of integrated into a program across several features of it, not just the supply of electrodes. Size of the sensing area. What's wrong with R&D screen printed electrodes? If you try to put a drop of blood on an R&D electrode, you actually find that the sensing area is bigger than the drop of blood. It's just too big. And I'll have and then there's also a sort of lack of support. I've sort of mentioned earlier on that at least 4 things have to be thought about when making something like an IVD, an in vitro diagnostic, on top of a screen printed electrode. The screen printed electrode itself, the functionalization of the screen printed electrode, the excitation of now sensor, and the extraction of information from the raw data. And at ZP, we do understand those 4 parts at least. And so when you're going to somebody and they're screen printing for you, they're not necessarily thinking of it in that holistic fashion. They can't necessarily support you. I have a little tab here which says cost versus scale. So I do have some calculators on the website, so I'm just going to drag that across now and just go to knowledge base, go to online calculators, go to sensor and cartridge price calculator, custom SP on flexible substrate with functionalization. Now, what we try to do on this page is, if I put in a typical length of an R&D sensor, so a length of 30 millimeters, width of 10, that means that you're producing, let's say, 139 sensors per sheet. So if you produce 20 sheets, you're actually only producing 2,780. Now this is a functionalized electrode. So when I say functionalized, it could be functionalized with ferrocyanide, it could be functionalized with Prussian blue, but it's functionalized in some way. So the cost per sensor is actually something like 15 USDs, 15 US dollars per piece. I need to back up slightly. Before you actually use this calculator, you do have to go through something called an NRE. So I'm just going to jump to this and just say there's NRE and then there's manufacturing. So NRE is not a term that I think is overly used in the screen printed electrode world, but it's used everywhere else, which is non-recurring engineering charge. Before you can get a manufacturing price, you have to go through an NRE phase, and an NRE phase is what's your questions, what's the answers. It's really a consultancy as well, giving people advice. So there's that whole sort of Q&A session. There's also the actual engineering work that has to take place. There's also the contractual agreements. There's also the quality system, especially if you are an ISO 13485 business and Zimmer Peacock is an ISO 13485 business, then there needs to be a quality agreement, which is paid for during the NRE phase. There's production, there's testing, there's packaging, how we're going to send this stuff to you, etc. So there's definitely an NRE phase. Then you can jump into this part, which I was just sort of prematurely jumping into a second ago, which was actually calculating the cost when you've gone through the NRE phase. So let me just jump back to that NRE, back to the cost phase. So I suggest that rather than going for large footprints like 30 millimeter length and 10 millimeters width, because that will give you, at low volume manufacturing, a price of something like 15 US dollars, you really need to go 25, 7, and that will immediately then jump you up to a manufacturing volume of more like 4,780. Even at low volume, that will then bring you to a price of like, 879, let's say. And I need to do something else, which is show you how this would then scale, for example, with volume. So for example, if you go to more like 10,000 sheets, then it can potentially come to 14 cents each. But you have to go through that NRE phase, because this is just a kind of a calculator that tells you, if you really want to get like a low price, go to 20 millimeters, and suddenly, now you're down to more like 10 cents each, for example. I'm going to jump back to the slides themselves, which are here, and I don't want to say plow through it. Size matters when it comes to cost. I know I've just sort of discussed that, but a glucose strip is not actually that big a device. Our devices that we like to sort of make, 7 millimeters by 25 millimeters, are also not that big a device. Some of these, one of these is a competitor, one of them is ours. They don't translate well into manufacturing because they're too big, and I've already run that calculator this morning. The questioner is really asking about circular versus rectangular, and the reason we do rectangular as opposed to circular is really about microfluidics and bringing the sample to the sensor. So here's a circular electrode, here's a rectangular electrode. R&D scientists like it because they can just kind of drop on their functionalization, let that cure or dry in some way, add on the sample. It's all very simple, you just can just pipette on. We can also pipette on as well. We just happen to pipette on like this. And because we're in this rectangular format, then we can then build these microfluidic chambers on top. And we also build much more complicated structures on top. So we're not making these rectangular structures because we like it. We do like it, but it's because we're actually thinking ahead as well of where, if it's going to be a product. And I'm going to show you on a couple of slides now about capillary fill. So the question the question to me is, why are your electrodes rectangular, not circular? And my question back is, how you intend to bring your sample to the electrodes? And I'll show you that, rectangular is a pretty good shape, because you can see that these rectangular electrodes actually fit really quite well then into a sort of microfluidic chamber, as we're showing here. I'm showing a couple of examples here. One of them is like a single sensing system, and the other one is a several electrodes all on a sort of credit card format, and they basically fill as the solution comes down. So the reason that we're rectangular is because we're actually thinking about how this is going to really play out in an actual product. Whereas I think a lot of these R&D electrodes with just the circular electrode are not thinking, how's a real product going to work? They're just essentially built for the R&D phase. Let me go a little bit. I don't want to say I need to go quicker, but I'll go forward a bit. Now, when you see this device filling up, you'll see that the way that actually there's a sequential sequence of events that one electrode gets covered, then the other electrode gets covered, and then the other electrode gets covered. I've got a video on that here. So in this video, essentially the blood is coming in. Whoops, a daisy. It's covering the first electrode, covering the second electrode. It covers the third electrode and completes the circuit, at which point the signal jumps up. This is called a fill trigger. So our electrodes have a shape because we're imagining them in a microfluidic chamber, for example, or channel. And they also have a layout that allows us to do what's called a fill trigger. I absolutely don't think that these circular electrodes that are very commonly used in R&D are designed in any way for this kind of fill trigger type mechanism. Because what happens is if you make it a real assay, the sample goes on, the sensor fills, and the assay essentially should start automatically. There shouldn't have to be a user interaction. And if you try to imagine how you're going to do this kind of fill trigger with standard R&D electrodes, then other than ZPs, it's not clear to me that they're even considering this requirement in a real product, let's say. Sample size, just to say this is a drop of blood. It's my blood. I did it with a single finger prick, put the blood on. Then you can see that actually our size allows us to essentially sample or deal with a single drop of blood. So some of these R&D circular electrodes are simply just too big to really even do this. I'm going to stop now and actually go into the next question. And the next question was really around measuring lactate in sweat. So at Zimmer and Peacock, we have, how do you measure lactate in sweat? Well, we have several components. We first of all have the lactate sensor itself. Again, we have microfluidics, and as in our previous question, our sensors are designed to be in microfluidic channels. And we are able to put microfluidics on top of it. Those microfluidics can be made from adhesive material, so we know how to attach those to the skin. And in this particular, we have actually generation 1 and generation 2 lactate sensors. So here I'm describing a generation 1 lactate sensor where we've got enzyme immobilized and we have a barrier layer on top of that. The barrier layer helps to protect the enzyme and also helps to kind of mechanically protect the entire stack of materials. Within the enzyme layer, there's a specific reaction which produces us, in the generation 1 sensor, produces us hydrogen peroxide, and we're able to detect the hydrogen peroxide. So I know I'm talking about measuring the lactate in sweat, but I just want to kind of give a bit of a science to what's going on in the background. I'm using the word here glucose and lactate, but you can have what's called a generation 1 sensor. These are fairly easy to make. They can suffer from interferences. There's generation 2, which we also make as well. They suffer less from interferences, but there's more manufacturing stages. At the moment, we don't make a generation 3 glucose or generation 3 lactate sensor where it's just a direct transfer between the electrode and the enzyme. I don't think generation 3 actually adds a lot of value. The value is probably in the IP position, but I'm not a great proponent of this at the moment. So we're here to talk about how to measure lactate in sweat. So we have a willing volunteer in the image. This is our site in Norway. The willing volunteer is had what we call an MVP, a minimally viable product put onto him. This is a lactate sensor. It has 2 parts to it, the electronics and the sensor patch itself. Thankfully, we live in a modern world with Bluetooth, so we're actually able to make, in this case, a Bluetooth connection to the laptop, and we are able to, whoops-a-daisy, generate a lactate profile. And I would just describe that lactate profile here. So we have the start. We have the point where the volunteer was first observed to be perspiring. and we have a point where they are actually reporting stress, and then not long after that, we actually get this actual lactate signal. And it's really interesting because, first of all, I have to make a disclaimer. This is not my data. This is, I believe, Joseph Wang's data. But it's very interesting, actually, that in his studies, he hasn't done concentration per millimolar. He's left it in microamps, but he actually gets a really similar profile. And then I was attending a webinar the other day, and there they also showed some data which had a really similar profile as well. So that was kind of, super reassuring. So if I was to summarize this, screen printed electrodes. Why are ours, for example, rectangular and not round? Well, round does help you in the R&D phase, but actually we do our R&D phase on rectangular. Rectangular is really future-proofing you for actually making a manufactured product. And then you'll notice also that we also think a lot about the cost at scale to manufacture these things. And so we have a certain sort of footprint. We try to keep things fairly small. You can't make them so small that people can't handle them. But the smaller you make them, essentially, the higher your manufacturing density and the lower your price. And then at Zimmer Peacock, we do have the entire technology stack to actually measure lactate on people. And if you have any questions about that, I would essentially reach out to us. And I just want to say thank you very much. So like I say, we do like to do these. First of all, we like to do them at the right time, which is 8 a.m. London time. This week we've done it at the wrong time. And we also like to do it live. We like the spontaneity of liveness. But this week, this happens sometimes when we're traveling. The Wi-Fi is just not up to it, so I've had to unfortunately record it. But thank you very much, and I hope you, if you're a regular here, you actually managed to find this. Okay, thanks very much.